I designed an experiment that needed 1,384 people in each group. Then I changed one thing about how I would analyze it, and it needed 300. Same question, same answer, same confidence. The difference was $16.6 million. I found it before I wrote a single line of model code. This is not a pharma trick. If you run a B test, if you run a pilot, if you hold out one region to see whether a campaign worked, you can use this at your job this week. I will also show you where I got it wrong. Here is the setup. Drug companies send sales reps to visit doctors. The question is whether the visit actually causes more prescribing. I built the observational answer first on public government data. 24.9 million rows scanned, 487,000 doctor year records. The raw comparison said promotion adds 56.5 prescriptions a year. Then I corrected it, matched comparable doctors, compared growth instead of size, removed the trend that was already there, 56.5 fell to 5.2. Then I ran the test that decides whether any of it holds. I measured the same effect in years where nothing happened. Those fake effects came back at 5.9 and 7.0. My real corrected number was 5.2. Read that literally, and I cannot rule out that the true effect is 0. The only fix is an experiment. Experiments cost money. So I priced 1. The sample size formula is this: n per arm equals 15.68 times sigma squared divided by delta squared times 1.35. Sigma is the noise, not the effect, the noise. Delta is the effect you want to be able to detect. And that constant 15.68 is not arbitrary. It is 2 times 1.96 plus 0.84 squared. 1.96 is a 5% false alarm rate. 0.84 is 80% power. The whole constant is just how sure you decided to be. My first version used the wrong sigma. I measured how much doctors differ from each other. That number is 137.61. The doctor at the 25th percentile writes 20 prescriptions. The 90th writes 187. The largest writes 8,965. So I was hunting an effect of 17 inside a population that naturally varies by 138. The formula said 1,384 doctors per arm at 17 prescriptions each and $900 a prescription. That is $21.2 million of revenue given up. Then I asked a plain question. I do not have to compare their levels. I have a year of history. I can measure how much each doctor changed. Think about testing whether a vitamin makes children taller. Measuring everyone's height at the end is hopeless because children naturally differ by 30 centimeters and the vitamin might add one. Measuring how much each child grew is easy. Growth varies far less than height does. Same experiment, different measurement. The standard deviation of the change is 64.06, not 137. Everything permanent about a doctor cancels out the moment you subtract. Here is why that is worth so much. Sigma is squared. The noise fell to 47% of what it was, and 47% squared is 22%. So the sample falls to 22%. 1,384 becomes 300, 21.2 million becomes 4.6 million, $16.6 million saved on a $900 per prescription assumption that I state openly because it is an assumption and not a measurement. And then I found the flaw in my own headline. That row is sized to detect 17 prescriptions. My own analysis said the real effect is 5 to 12. Power against 8.5 is 29%. So the honest recommendation is the next row up, 1,200 per arm, 9.2 million, twice the money, and the cheapest design that can actually answer the question. 3 things you can take to work. 1, if you have a before period, measure the change, not the level. Each subject becomes their own control. 2, sigma and delta are both squared. Halve the noise and you quarter the sample. Halve the effect you are chasing and you quadruple it. 3, size the test against the effect you actually expect, not against a round percentage. A power calculation with no prior estimate is arithmetic, not design. All of it is public: the code, the numbers, and the part where my own model failed its evaluation and refused to output a targeting list. Link in the description.